This tutorial is about vector field and how we can plot various vector fields in MATLAB. So just like we created images in the 2D scalar case, we can create a mesh grid. I've created a mesh grid that goes from -1 to 1 at a spacing of 0.25, and then the same values are plotted against both y directions. So I have ordered pairs on -1 to 1 grid. So let's look at some of the examples of vector field that we talked about in the class. So the first one we talked about was xi plus yi, and if you remember this, as the x and y values increase, so does the length of this vector increases, because bigger numbers means bigger vector. So at point 1 1 we have a vector of 1i plus 1y, but at the point 2 2 we have a vector 2i plus 2y. So the x component we call it u, and y component we call v, and so now we can create these two vector components that are u is equal to x and v is equal to y. And we learned about the quiver command in one of the labs. This quiver command can be used to plot all of the vectors. So this quiver command is saying that plot at x and y coordinates u direction and v direction components are given, and create a vector from these components and put it at x and y location. And in our case we have we look at our size, we have 9 by 9, so there are 9 vectors at 9 locations. So if we plot this, we see all of those 9 by 9, 81 total vectors. And as we visualized in the class, you can see as you go away from the origin, the length of the vector increases and it's pointing away from the origin. And this is a diverging field, a diverging vector field, where we have some kind of source here, could be an explosion, could be a source of some fluid, and all the material or field value is moving away from this diverging point. Now we can also look at another field that we talked about, that was yi minus jx. So in this case the x component is y and y component is minus x. And now let's plot this one, and remember we said that this was a vortex, and you can see how this field is all going in a curl around the origin. And so this field has a certain curl associated with it. And this is how you can visualize a 2D field. At each point I have an x component and a y component of the vector. Now the same idea can be extended to a 3D field. So here is an example of a 3D field. It's a velocity field of a fluid. Here's the x component, here's the y component, and here is a z component. This is actually minus z component of the field. So just like we did 2D case, we can create a 3-dimensional grid using the mesh grid command. So let's clear our previous variables and create this 3-dimensional grid. So you can see this is a 7 by 7 by 7 grid in 3 dimensions, and then we define the three directions or 3 components of the velocity vector u, v, w based on these equations, and now we have a 3-dimensional field. So just like quiver command, we can use quiver 3, where we have to give the z coordinate as well as the z component of the velocity, and this will plot the arrows in the 3 dimensions. And now you can see that this is a 3-dimensional vector field, and you can kind of get a feel of how the flow is happening. You can see that the flow is going in general in this direction, but you still can't see very clearly if you look at this view, you can see along the z direction, this fluid is also moving up and this fluid is also moving down, but this one is moving straight. So maybe there is some kind of flow going like this, but it's not clear from the quiver command. So we're going to look at some other ways to visualize this vector field. The first one is called cone plot. So a cone plot basically puts cones at specific points. So I can define a grid at which I want to place the cones. So I want to place the cones at -1, 0, and 1 along each axis. And I can create this. So you can see this will be a 3 by 3 by 3 kind of grid. And it's going to be -1, -1, -1, -1, 0, -1. So along x-axis, along y-axis, so there'll be 3 times 3 times 3, 27 points at which these cones will be placed. So when you run this cone plot command, you're telling it that at x, y, and z I have field u, v, and w, but don't plot all of those x, y, z, but only plot at these locations some cones that show me the direction and magnitude of these vectors. So once we run this, you can always change the view a little bit if it doesn't come across correctly. So you can see there are 27 of these cones, and at each of these locations the cone is telling us the magnitude of the vector and the direction of the vector. So this is a little bit better plot, a different view of the same field. The advantage of using cone plot is that we can associate color with these cones as well. So for example, we can assign a color based on the magnitude of the vector. So I can add the W, and if you remember, this is the magnitude of the vector. So u squared plus v squared plus w squared all square root is going to give me the magnitude of this vector. And now I can plot the cone plot, but at the end, the last argument, which is the 10th argument, is the color of the cone. So it's the same command that we did before, but with the color added to the command. And you can see now the smaller vectors have blue color and the bigger vectors have red color, and the whole range within. And the way we learned last time, you can always use the color bar to show what the colors represent. Okay, so this is another way of visualizing a three-dimensional vector field. Now, still we didn't get a very good feel of how the fluid was moving, and if you remember from your fluid mechanics, you can follow the path of a particle. So if I go back to my quiver plot, and I can look at this point right here, and I can follow it. If I can follow that point, and I can follow the point that where the velocity of the point is, always tangent. That line is called a streamline. And so we can also create streamlines in this, but I have to tell it from where do I want the streamline to start. So if I give a starting point, this can tell me the streamline. So let's say we tell it that we want to, let's hold on this plot, and we say that we want to create a streamline that starts from -1, -1, -1.5. So this is -1.5 along z, and then -1 and -1 would be somewhere here. So let's run this. So you can see how this has shown me a line through this plot that is showing that if the point from here, what is the shape of the streamline. And I can have multiple points here. So that's what this next part does. It shows us what so this part just shows, we'll put a red circle at the point where the streamline starts from. So this particle right here, I'm starting a streamline from this particle and looking at its shape. But I can also create many points. So here I'm creating, so minus 1 to 1 will be 3 points. So I'm again creating 27 points, and I am going to create streamlines from all of these 27 points. So you can see there are 27 streamlines from minus 1, minus 1, minus 1, and at a grid spacing of 1 from this location in all direction. I'm creating a stream. Okay, and now you can have a little bit better visualization how the top stream, from the top plane the streamlines are coming down, and from the bottom plane streamlines are coming up. And let's go along this direction. You can see also they're coming inwards. So you can imagine there might be a little converging point here. Could be a pipe entrance, and all of the flow is happening towards that. And so if I run all of these commands together, here you can see the starting points as red circles with this command, and I can also hold on and put the quiver 3 command in red color, and now you can also see the whole vector field along with the streamline. So it gives you a little bit better perspective of how the fluid is moving in this vector field. Now we can also pass some slices through these this vector field. So here is a command, just like the slice command that we did earlier. What I'm saying is that I have a vector field defined by XYZ and UVW, and then I want to pass a slice in the Z perpendicular to Z axis at minus 1.5, and you can see that this is that slice. This is the slice at Z is equal to minus 1.5. I can do the same thing, and I can say I want to pass a slice at minus 1.5, and then maybe 1.5 in the y direction. And so you can see how this gives you a slice in a plane and gives you a little bit different perspective of how the fluid is flowing when it is restricted to this plane or restricted to this plane. And we can also look at the x-axis at 1.5. So you can imagine these as the bounding box planes of this field, and this, you can see how this perspective gives you that all of this fluid or flow is converging to this point, and here it's also converging to the middle part, and here it's also converging to the middle plane. So the feeling that there might be a converging point here becomes a little bit more clear from this slice plot. Now we can now improve based on this. Now we know that all the streams are kind of converging. We can improve our visual by changing the streamline plot that we earlier did. Instead of having a streamline starting at every point, we can only start it at the x is equal to minus 1.5, which means only the first plane. And now if we plot all of these streamlines, you can, and let's put the red circles as well so we can see where these are starting from. You can see that I can only create streamlines from this plane, which is x is equal to minus 1.5, and from this plane all of these streamlines are converging to a central location as it moves along the x direction. So this kind of concludes the vector field tutorials. I have two other commands that you should try. One is called stream tube. This gives us a feel of the divergence of the vector field. See how the tube is becoming bigger as the streamlines converge. And the second one is called stream ribbon. And this gives us the curling of the field, as you can see how this forms a ribbon, and the ribbon twists and turns depending upon how it is changing along the direction. So stream tube and stream ribbon give us divergence and curl as the vector field moves forward.